Now this is going to be a little bit more experience with the first law of thermodynamics and the math that goes along with it. Okay, yesterday I left off talking about this equation right here. Q equals M delta T C. Okay? Now first of all, when we talk about Q, Q is the heat that is in the sample. The amount of heat that it has, the thermal energy contained with the sample. That can be measured in calories, it can be measured in joules, it can be measured in BTUs. It doesn't matter which one you have, but the only thing it is going to matter is this C value over here is going to be different for the different values. It all comes back to just basic conversion between calories, joules, and BTUs, which I'm going to recommend that you write those down in your notes. It's on the same page, or the page before it talks about this equation right there. It is incredibly useful to be able to bounce back and forth between them because you're not always given this in more than one form. So sometimes you're going to want to even convert your standards, your solids that you already know. Okay? So the Q is the amount of heat. M is mass of sample, the amount of stuff you have. Now, once again, this can be in grams, it can be in kilograms. It depends on what reference you look up, which one you're going to want to use. Okay? Delta T, this is your temperature change, but the important thing is it always, 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 always needs to be in units of Kelvin. Alright? Nice thing is 1 Kelvin equals 1 degree Celsius, but it's important to know that you should have this in Kelvin. Okay? And C, this is what is called the specific heat of the metal, or material in general. Now the specific heat is basically a handbook value. This is something that has already been worked out. Most materials have a slightly different C value, but this is something that you can look up on the internet in that CRC Handbook of Chemistry and Physics, that big thick book that I have from like 1965 over there. That is something that you can look up. Alright? Now this thing right here is going to kind of set your units. A lot of times you're only going to find one form of it, and then you're going to have to set the rest of the equation to those units in order to make it work. You have to be precise, you have to be deliberate, and you have to look at exactly what you're given. Because if you're using grams here, calories here, Kelvin here, and this is in kilograms, joules, Kelvin, it is really going to screw your stuff up. Okay, so pay attention to your units. Alright, now we did a couple of math problems with this. Basically, it's just a plug and chug. You need to identify what you have and put it in there. Okay, now the next part that was giving some of you guys some trouble was one of those problems was talking about melting silver. But if you have melting or freezing, if you have boiling or condensing, what ends up happening is there's a certain amount of heat that is required or that must be removed in order to go from one state to the next. It requires a certain amount of heat to go from a solid to a liquid. It requires a certain amount of heat to go from a liquid to a gas. So because of that, if you were to look at a graph of temperature versus time for a sample, let's just say of ice water, okay? You take a block of ice. Originally, that block of ice is going to have some temperature. It can be below zero. So let's say it starts down here at, let's say, -20 degrees Celsius. I know I'm using Celsius, and we normally use Kelvin, but this will just make your life easier for this part here. Now what's going to happen? The important parts of water, important temperatures, it is going to freeze at 0 degrees Celsius. It is going to boil at 100 degrees Celsius, as long as we're under STP conditions, which is standard temperature and pressure conditions. We're going to talk later when we start getting into the second law of thermodynamics about how the pressure is going to change things, how volume is going to change things, and how entropy is going to change things. But for right now, we're just assuming that we are at STP conditions, standard temperature and pressure. So, as you heat your sample of ice, it is going to have a roughly linear heating process until it gets to 0 degrees Celsius. Once it gets to 0 degrees Celsius, it needs to collect a certain amount of energy in order for that solid sample to turn into a liquid. Because of that, the temperature is going to level off for a moment. Once it has attained enough energy for it to bump up to the next state, then it is going to be able to heat up again. And we're going to be talking about a liquid here. It'll maintain a liquid until it gets up to 100 degrees Celsius. Once it gets up to 100 degrees Celsius, once again, that temperature is going to level off. It needs a certain amount of energy in order to get this thing from one phase into the next. And then from there, you can continue to heat it beyond there, up to its critical value, but we're not going to worry about that for right now. Now the thing is, when you're talking about these slanted regions right here, the slanted regions are going to be where Q equals M delta T C. In this phase, when it is in the same material phase, it is going to have the same specific heat value. Interestingly enough, the specific heat value for water is slightly different than the specific heat value for ice, which is slightly different than the specific heat value for steam. So, anytime that you're at a slanted region here, you need to do Q equals M delta Tc to find the total amount of energy required to actually bump it from one stage into the next. Alright? Now, when you have these flat portions, the flat portions are going to be where you're doing your Q equals latent heats of times your mass. Okay? Now, that's what we had to do when we were talking about that silver sample. That silver sample had to completely melt. Now, it told you the boiling point, all that lovely stuff was given to you, but the thing is, sorry about that. Right. The thing is, if you're going all the way through the state, you need to figure out exactly how much energy is required to go through it. Okay? So, just realize, anytime that you're within the same sample, the same material, same state of material, you can use that same C value. But as soon as you switch it from one material or from one phase into another, your C value is going to change. Okay? Now, the big question and the big reason that we're actually covering this, because a lot of times it comes down to it, you're looking at this, I already learned some of this in chemistry, why do I even care? The thing that gets interesting is when we start getting into the first law. Now the first law of thermodynamics, we're just going to call it first law of thermo here, basically says that any change in the internal energy of your sample is going to be due to one of two things. The internal energy can be increased by adding in heat, or it can be decreased by taking out work. Okay? Now, this is kind of the thing that is most interesting here. All right? Work is what we're really, really concerned about. Without that work quantity, we're not going to be able to have refrigeration. We're not going to be able to have air conditioners. We're not going to have anything that actually moves heat from one area into another. All right? The understanding of all this is that work. There's certain thermodynamic processes that are going to allow you to pull work out of a sample. Things such as Stirling engines, which we'll work with a little bit later, or where we can actually pull this stuff out. Now, realistically, if we look at some of the stuff that we've already done here, Internal energy, that is just all of the energy the sample has. It can be in the form of potential, it can be in the form of kinetic, it can be in the form of, well, that's pretty much it. But it can be in either of those two forms. Now Q is heat, also known as thermal energy. All right. And work is applying a force that causes some type of displacement. This is the part that matters. Okay? Now, in this case here, the force times displacement, sometimes we are going to actually have something that's propelled forward. Sometimes we're just going to have to move energy, move heat from one place to another. So this is not always going to be what it is. But let's look back at what we already know. We already know from the law of conservation of energy energy cannot be created, it cannot be destroyed, it can only change in forms. Okay? So all of the energy in here can either be turned into heat, or heat can be added to increase the amount of energy that's in there, or we can take that energy and turn it into work, because energy in its definition is the ability to do work. So that means that one of two things can happen. We can increase the energy with heat, we can decrease the energy with work. Okay? Now I hope that made things a little bit easier. What I want you guys to try now, and these are homework problems that are going to be due Tuesday of next week. It is on page numero 501. Numbers. Oh, where'd they go? Let's do 24 and 26. And let's do 27. Now for 27, you're also going to need to remember what the definition of power is, which is the amount of work done over time. Okay? If you're struggling with these, please let me know on Monday. Please try these early. I'm telling you right now, this is becoming a college course. And I'm seeing a couple of you a little bit too laid back for it. It is going to bite you guys hard. Period. Pay attention to this and stick with it. All right? Enjoy, and we'll see how this goes.